New chapter. I believe it's chapter 5. We're starting in on recursion. And this is a topic that you have already seen in Computer Science 211. We've discussed this in class. It tends to be not a very favorite topic for folks, and I hope when we're done with it here, it will be your favorite topic. Recursion can be confusing at times. I think the problem that you may have encountered in Computer Science 211 is there weren't any really good examples of when you would use recursion. And there are going to be some good examples of it here. We're going to see that there are times that recursion can actually make your life easy. Although actually we're not going to see it in this chapter. We will see it when we get to the next chapter on trees. But now's a good time to get comfortable with recursion. So what is recursion? I tend to think of recursion as the dog chasing its tail. You might have some method in here, already starting off badly, int goo, and we might come in here and inside of here, inside this method, we're actually calling goo. So it almost looks like we're doing something that looks like this. And of course the problem just in this right over here is this could potentially be an infinite loop. Potentially an infinite loop. Not a good idea. So let's look at an example that I'm sure that you're all familiar with already, and that is this notion of factorial. Okay, this may seem like a trivial example, but it's a good example, at least for seeing some of the ideas here. So first of all, we know that in math, we write it this way, and we can say that that's equal to n times n minus 1 times n minus 2, all the way down to times 1. Okay, but we also note that this is equal to n times n minus 1 factorial. In other words, we will note that this quantity right over here is in fact n minus 1 factorial. Just like that. So our first stab at this is if we were to do something like a public static int fact int n, we might come in here and we might say something like the following, or we could say just return n times fact n minus 1. Okay, and close it up. And of course the problem that you have here is that there's nothing that really stops this. So if I were to do fact 3, that's equal to 3 times fact 2, but that's equal to 3 times 2 times fact 1, but that's equal to 3 times 2 times 1 times fact 0, but that's equal to 3 times 2 times 1 times 0 times fact minus 1. And you can see that this is going to go on for and ever and ever. In other words, what we haven't done in here is we haven't provided what is sometimes referred to as the base case. You need something to make this thing stop. And sure enough, we know that a proper factorial would be something like the following. Public static int fact int n, and we would come over here and say something like the following. If n is 1, return 1, else return n times fact of n minus 1. And you can see now what we have over here is over here we have what's referred to as the base case. And what this will do is this will stop this, this infinite looping. So that if I do fact 3, well, fact 3 is equal to 3 times fact 2. But fact 2 is equal to, so that would be 3 times 2 times fact 1. And finally, when we compute fact 1, it's going to return 1. So that's just 3 times 2 times 1. And ultimately, what would happen is a 6 would get returned. Okay? There are a couple of things that I want to point out about this particular thing. I want to focus in on this line over here. Could I have written it this way? Could I have said return fact of n minus 1 times n? In other words, taking these two factors right here and just switch them. And the answer is yes, but this one is preferable. This is an example of what is called tail recursion. And what tail recursion means is it means that the recursive call is the very last thing in the method here. Okay? Whereas over here it wouldn't be the last thing, we'd be multiplying by n. And it would take me a very long time to explain precisely why this is better, but the partial answer is that compilers can optimize this much better. In fact, very frequently when a compiler sees something that's tail recursive, it'll just rewrite the whole thing as a loop. And loops tend to be faster. So the point is, I want to point out that tail recursion is preferable if it can be done. There are times that it can't be done. The other thing that I want to point out about this method here is that this method here is single recursion. And what that means is that inside of the method, we only make one recursive call. We're going to see an example in a few minutes that's actually doubly recursive. And you can have triply recursive. There's no limit on how many recursive calls you can actually make inside of a method. Now, I want to draw a picture for you again. So I want to assume that I have, and I think this is very helpful what I'm about to do. It's not entirely accurate, but I think it'll help you sort of conceptualize what's going on. I want you to imagine that I've got a public static void main. With all this other stuff in here. And someplace in here, I come over here and I say x is equal to factorial 3. And then there's other stuff in here. And finally it ends. Now what I want to do is I want to give you sort of a conceptual idea of what's going on in memory. Like I said, this is not actually true, but it's conceptually true. Maybe that'll become a little bit clearer as we see what's going on. Now, what's going on in memory is, first of all, I want you to think about a very large stack of memory. And here it is. I'm drawing it here. And what's happened over here, so this is a stack, and I want to pretend that the stack is growing that way. And you could think of this code is residing somewhere here in memory. So I've got my public static void main, and I hope you'll indulge me and let me use these abbreviations. And someplace in here, I have come along and I have said that x is equal to factorial 3. And then there are more statements, and then this ends. And this is on the stack. And the point is that this will not get popped off the stack until I hit this closing brace right over here. Now, what's happened here is I'm calling this thing called fact. So what's going to happen over here is I've got this public static int fact, and I came in with a 3, and inside of here I said if, and now I'm going to replace the parameter with the actual value. If 3 equal 1, I'm going to say return 1, else return 3 times fact 2. And then there's this closing brace. Now I'm going to have fun here with colored pencils. And what I want to do over here is I want to indicate that over here, whatever I'm reading out, that means that's executed already. And I'm waiting for this to come back. Now I've come over here, and in here I've executed this. And I'm over here, but over here I still haven't completed this statement yet because now I have to call fact 2. So what's going to happen now is I go back onto the stack, and now I have this public static int fact 2, and inside of here it says, okay, if 2 equal 1, return 1, else return 2 times fact 1. And here's my closing brace. And again, what's going on here is this hasn't completed yet. What's happened over here is I've completed all of this, but I haven't completed this statement yet. Okay? Now what's going to happen is I come over here one more time, and you can see up here, there is my public static int fact, and now there's a 1. And with a 1, okay, I come in here and I go if 1 equal 1, return 1. There's this else, and there's this other stuff here, and there's this closing parentheses. Now what has happened here is I finally hit a return statement and I'm returning a 1. This finally ends, okay? I get down to the closing brace here. The return statement basically ends the whole thing. And what is the effect of that? The effect of that is that I am now going to send a 1 over here, and this stack now gets popped. And I wish I could erase quicker than this, but I think you all get the idea. And now what happens is with the 1 being passed over to here, okay, this now happens. Now this calculates to be 2 times 1, and I'm going to return a 2, and I hit this brace here. So what's going to happen now is a 2 gets sent over here, and again, now I can pop this stack. And again, I apologize for the mess, but I hope conceptually this all makes sense to you. And now when I get over to here, this thing over here has now returned the value 2. Okay, so I go 3 times 2 is 6. That means I'm able to return a 6 over here. I've hit the closing brace, I've executed the return, and that means that this memory now also gets popped off the stack. So now I am back to this. My stack is just this thing over here. I make the assignment over here, x gets the value 6, and I keep executing this program until I hit the closing value. All right, I want to consider something I want to add to this a little bit. And this shouldn't be too hard for you to follow either. I want to rewrite factorial. And I'm going to come over here. I'm going to say public static int fact int n. I'm going to do something. I'm going to just declare some variables in here. They're not going to do anything very interesting, but I just wanted to show you the effects of declaring variables. So I'm going to come in here and I'm going to say int a, and I might say char b, and I'm going to come over here and I'm going to say double c equals new double 10. And then I'm just going to come in here and say if n equal 1, return 1, else return n times fact n minus 1. And again, I want to assume that somewhere in main here I've said x is equal to fact 3. So again, this is the whole point of this slide right here is just to talk a little bit about what's going on in memory. So first of all, what's going on over here is here's my public static void main, if you will. And here I'm saying my x is equal to fact 3. And what's happening over here is here is my fact 3. And it's coming in. And the point is that it's going to save space. Okay? It's going to come over someplace in here. I'm going to draw it after the program. So it's going to come over here and it's going to go here's space for A. And here's space for B. And here's space for C. Okay. And I'm going to say this is data for fact of 3. And we all know that we come down in here and at some point it's going to come over here and we have this call to fact of 2. And what's going to happen is we come over here and here is fact of 2. And again, what's going to happen is we're going to declare some space in here for A, and for B, and for C. And these A, B, and C have nothing to do with these A, B, and C. And at some point in here, there's this call to fact 1. And again, up here, way up here, fact 1. And again, there is going to be an A. There's going to be a B, there's going to be a C, and over here we do my return 1. When I do my return 1, what's going to happen is I'm going to pass the value 1 back to here, okay? And what happens is I'm going to pop the stack. And not only does the code go away, but the variables go away too. So that I'm now in this situation right here. I wish I could make my eraser bigger. Maybe I can. What happens if I do that? Oh, that's a much bigger eraser. What do you know? Okay, and then what happens over here is I get over here, and this now returns the value 1, which means that a 2, whoa, and now I have that. A 2 gets over here, and I'll erase because now I popped this stack. And again, these variables go away as well. So that's what my stack looks like. Okay, and then over here, I get 2. This evaluates to be 2. So I'm going 2 times 3, which means I can now send the value 6 over to here. And again, what happens is I pop the stack and all of these go away, including the variables. Okay, so as I've indicated to you, what I've just drawn for you is in fact not what happens, okay? But I think it makes it easier to visualize or conceptualize how recursion is working. So what in reality does happen? Well, it is true that as I make these recursive calls, I will continue to allocate these variables on the stack, ABC, ABC, ABC. What I don't need to do is I don't need to keep repeating the code, okay? But I thought that by showing it to you this way, it would be much easier to visualize.